What determines if someone will respond to cancer therapy or not? A cancer diagnosis is often one of the most distressful events in someone's life. There is a lot of uncertainty, especially at the beginning. When a patient chooses a treatment, they will often do it on the basis of a treatment response rate, which is the percentage of chances that the treatment will work. Let's say the treatment response rate for your given treatment is 50%. As a patient, it might feel like a coin flip to you. It might feel like it's perfectly random. You have a 50-50% chance of your treatment working or not. However, cancer biologists agree that this might not be true. There might be determinants that we can know ahead of time by screening your tumor that might tell us if the treatment is going to work or not. If we could improve our certainty about whether a treatment will work or not before performing the treatment, the way we treat cancer could improve in two major ways. First, clinicians could give better information to patients and better guide them in their decisions of treatment. Second, if we understand why a treatment doesn't work by knowing the biology underlying it, we could, as researchers, develop better treatments that do work for the patients that do not respond to the currently available ones. Welcome to Read With Me, the series in which I read papers and share what I've learned with you. I'm your host, Philip Carl. Read With Me is a project by Orders of Magnitude. Orders of Magnitude is a science communication organization whose goal is to share science with the general public. You guys have funded the research, and often scientific papers are obscure to you. So what we want to do is bring the science to you, walk you through the data, trust your intelligence, and just show you the great research that is done out there with your tax money. In this first episode of Read With Me, we will look at a paper published in Science Immunology. It's called Spatially Mapping the Immune Landscape of Melanoma Using Imaging Mass Cytometry. This study involved many groups, many of which are based in Montreal, but some groups who are also based in the US, so many researchers were involved. Please note that on the paper, the first 3 authors contributed equally to this work. The principal investigator of this paper is Dr. Ian Watson, whose main affiliation is with the Goodman Cancer Institute of McGill University, which is where I happen to study, so I'm very proud of the great research that is done at my research institute. First, a disclaimer. I am a biochemist by training. I have done my master's in biochemistry. I know a fair bit about cancer biology. I love to read papers, but I was not involved in this study. I am not an immunologist, and I might say things that are slightly inaccurate in the details here and there, but I hope that you can get the broad picture of this paper by my description here. Let's dive right into it. As most of you know, cancers start with a tumor. The tumor is a mass of cancer cells that grow uncontrollably. Eventually, the cancer cells can seed out of the tumor to other organs and form secondary tumors. This is called metastasis. Only after metastasis does the cancer become very problematic for the body. It can cause organ failure, and eventually it can lead to the death of the patient. Research that has been done in the previous years has highlighted that not only the cancer cells are important, but also the other cells that are found in the tumor. A lot of other cells can be found in the tumor, such as immune cells, blood vessel cells, and others. Some of these cells might help the cancer by giving nutrients to it, by promoting inflammation, which the cancer likes to some extent. Other cells, such as immune cells, can try to clear the cancer. To study the tumor microenvironment, or the cells that are within and around the tumor, we often use a technique called flow cytometry. Flow cytometry is a great technique that involves chopping up the tumor down to individual cells and then analyzing the cells one at a time. And then we can tell this one cell is a cancer cell. This one cell is an immune cell. By analyzing this, we can know what cells constitute the tumor microenvironment. However, flow cytometry has a tremendous limitation. It does not retain spatial information. You have to break down the tumor in the first step. So if, for example, the cancer cells are all clumped up in the middle and the immune cells are all around the tumor, you might have a different outcome than if the immune cells are intercalated with the cancer cells and have fully invaded the tumor. This is because cells usually have a limited radius of action. An immune cell often requires direct contact with the cancer cell to kill it. So this is what the authors of this study sought to find out. Is the spatial distribution of certain types of cells in the tumor important for a response to a given therapy? Let's get right into the question addressed by this specific study. In this paper, the authors and the researchers were interested in a type of skin cancer called melanoma. They wanted to know the determinants of response to immune therapy. Immune therapy, or immune blockade inhibitors, is a therapy or a drug that promotes immune cell or that encourages immune cells to kill cancer cells. So they wanted to know more specifically if the distribution or the abundance of a given type of immune cell within or around the tumor might have an impact on the response of patients to cancer therapy. They used this new technique that almost didn't exist 10 years ago, called imaging mass cytometry. As opposed to flow cytometry, imaging mass cytometry allows you to know the cell type, the activities of the cells, and the cell state without losing any spatial information. It is an amazing technique. I will not get into the details, but remember that it does the same thing as flow cytometry while retaining the spatial information. The authors hypothesized that either the abundance or the distribution of a given tumor cell type, they didn't know which one at the beginning of the study, could determine if the patient will respond well to immune therapy. The tumors from 67 melanoma patients were analyzed in this study. All patients were treated more or less in the same way. The tumor was resected via surgery, and then they started immune therapy. Then the authors analyzed the tumor and tried to figure out if there was anything about the spatial distribution of the cells or the abundance of the cells in the tumor that predicts if a few months later or a few years later the patients would respond. So how do we even analyze the tumor to start with? We have this tumor, which is some sort of solid mass. In order to analyze the tumor using imaging mass cytometry, we first have to slice the tumor in very thin sections of about 4 micron thick. So very, very thin sections. Then imaging mass cytometry, the magic of it is it allows us to know the abundance of 35 protein markers at very small regions. And by looking at the abundance of these markers, one very tiny region at a time, each of one being a pixel, we end up with a high resolution image of a section of the tumor. And that's amazing. So why 35 protein markers? Protein markers are just a way to identify the cell type, the cell activity, the cell state. It's just essentially a way to identify who is the cell and what it does. These 35 markers were measured in 200,000 cells. This is a lot of data. This is why the authors decided to first analyze the non-spatial information about the cell types, the cell activity, and then to analyze the spatial information independently. Let's start with the non-spatial information. What did we learn about the constitution of the tumor in terms of cell type, cell activity, cell state? The first thing that I found very impressive the first time I read the paper is that about half of the cells in the tumor were not cancer cells. That is a testament to how important the microenvironment must be if it makes up to half of the cells in a melanoma. If we focus specifically on immune cells, there were 8 types of immune cells that were identified in this study, or at least they were distinguished using the protein markers. Among them, the helper T cells, the T cells, the B cells, the macrophages, and the monocytes. Does the abundance on any of these immune cell types give us a good idea of whether the patient will respond or not to immune therapy? Well, in terms of cell type alone, nothing is significant. So no abundance of a given cell type by itself can determine whether a patient will respond to immune therapy. So what the authors did is they decided to further investigate the protein markers in order to see maybe if there was a subset of cells that were important. By using 3 other markers, they identified that proliferating, antigen-experienced, cytotoxic T cells were significantly associated with the response to immune therapy. Let me walk you through what these cells do. Proliferating means that these cells are able to divide, to proliferate. These immune cells are able to form more immune cells. Antigen experienced means that presumably these T cells are able to recognize a cancer. Cytotoxic means that they can kill cells or be toxic to cells. And T cells is just the cell types. Whenever you hear CTAE in the rest of this video, think about immune cells that are able to recognize and kill cancer cells and that are also healthy enough to proliferate. The abundance of CTAEs is very good at determining the response rate to immune therapy. Patients who had low levels of proliferating CTAEs in the tumor had a 0% 2-year survival rate, whereas the patients who did have a lot of CTAEs, proliferating CTAEs in the tumor, had a 45% survival rate 2 years after the treatment. This is the information we learned only by knowing the cell types within the tumor. But, as I told you, the thing that is groundbreaking about this study is the spatial information that was obtained using the new IMC technology. So a question remains, right? Is the location of CTAEs a good predictor of response to cancer therapy? Let's see. And this is where the most stunning part of the study comes into play. The authors made a map of the tumor where each dot is a cell and each line is the distance between a given cell and its neighboring cells. That's called a graph in science, but this graph, man, it's beautiful, especially the one with the dark background. They use a lot of computational analysis to find out what does this spatial map tell us about the response to immune therapy. Here on this map, the colors represent the type of cells. What does the spatial information reveal, especially about the cytotoxic T cell, the CTAE, that we were talking about earlier? Well, these antigen-experienced cytotoxic T cells, their median distance to cancer cells in patients that did respond was 60 micrometers. Whereas in the patients that did not respond to cancer therapy, that distance was 150 micrometers. This means that the cancer cells in the tumors of the patients that do respond all have a TCAE in very close proximity to them. Whereas in the patients that do not respond, some cancer cells are very far from the closest TCAE. This means that not only the amount of TCAE or proliferating TCAE is important, but also to what extent the TCAEs have invaded the tumor. Non-spatially, proliferating TCAEs are important. Their abundance is important for response to cancer therapy, specifically to immune cancer therapy. On the other hand, the distribution of these exact same type of cell is important for the response to the immune therapy. Specifically, they have to be very close to cancer cells in order for the therapy to work. Let's go to the discussion to find out what that means. After getting all this information, you might wonder, why is the position of CTAEs important for the response to immune therapy? One of the reasons for this is when you treat with immune therapy, it reinvigorates the cell's ability to kill cancer cells. However, CTAEs, in order to be able to kill cancer cells, have to be in close proximity to them. In fact, they have to have a direct contact with a cancer cell. Plus, cancer cells can recover from up to 2 contacts with a TCAE, meaning they require sometimes 2, sometimes 3 contacts with a TCAE to fully die. This means that most cancer cells within the tumor have to be, respectively, close enough to a TCAE for the immune therapy to work. It is very logical. Another further question you might have is, why do some patients have more invasion than others? The authors speculate that this might be a question of timing. At the beginning, all tumors might have invasion by a lot of antigen-experienced cytotoxic T cells. But over time, the T cells become more and more dysfunctional and less able to kill the cancer. Like for any good study, the authors in the discussion highlight the limitations. The biggest limitation that I found is that the technique IMC is still in its infancy. It means that before applying IMC in the clinic and actually use it to screen a patient, we will need the technology to develop a bit more. This is because, first, IMC is a very costly technique. The machine to do IMC is not available in all hospitals, and also a lot of computational resources are required in order to analyze the data. We can hope that one day, when a patient has a melanoma, we can extract the melanoma, slice it up, do IMC on it, and determine, is immune therapy the right therapy for this patient? And this is an incredible prospect. We hope to have more of these studies that are able to screen early in cancer. Actually, in personalized medicine, being able to screen a cancer early, being able to know if the patient is going to survive or not to a given treatment or respond or not to a given treatment ahead of time is the best weapon we have, because in that way, we can best inform the treatments we give to the patient. And eventually, we will be able to develop treatments for all subtypes of cancer. We will only have, once a patient is diagnosed, to figure out what type they have and what treatment is best for this type. Thank you for watching this first episode of Read With Me, this production of Orders of Magnitude. We're super happy about this new project and sharing the science with you. If you have any topics that you would like us to talk about in next videos, please leave a comment below. Also consider subscribing to Orders of Magnitude and consider just leaving us a little thumbs up. It would be greatly appreciated. Share it with your friend. Thank you very much, and we'll see you in another video.